Welcome back. Now let's apply this interference or superposition of waves, 2 waves, 3 waves added together to generate standing waves. Let's apply it to sound. The difference is going to be, or one of the differences is going to be that for a string, it's fixed on both ends, and the speed of waves on a string is controlled by the tension and the thickness of the string or the rope. The thickness meaning mu, the linear density. By the way, I should have had here 2 lambda 2 and 3 lambda 3. However, for sound, if it's in air, the speed of sound is fixed. That's 343. Okay? So it is 343 meters per second. So that's going to be a player. For sound, we're going to have instruments where you have let me get one. So here, for wind instruments or standing waves of sound, standing sound waves. So let me just write it here. Standing sound waves. So you have a tube, let's say, and that tube could be closed on both ends, closed, open, or open, closed. So let's say closed. So it's closed on this end and it's closed on this end, and then you can have, and then it's of a length L. It's of a length L. Now let's say you have something here that shakes the air to create sound waves. So what kind of waves would you have? Well, if it shakes the air here is not free to shake. When it gets to here, it's fixed, it can't move. It's a node here and it's a node here. Now what can you do? Between a node and a node, if you have a node and a node, you can have an antinode, or you can have a node and then the next node here, in which case you will have node, antinode, node, antinode, and then a node. So let me just show you, let me just write it here. You can have this. Node, antinode, node, antinode, node, antinode, and so on. And the distance between a node and an antinode is a quarter of a wavelength, one fourth of a wavelength. And the distance between a node and a node is half a wavelength, which is, if it's clear, if you go from a node to an antinode, you have this, that's a quarter. So the full wavelength will be this. So that's a quarter plus a quarter plus a quarter plus another quarter. So that's one full wavelength. So the distance between a node and an antinode is a quarter wavelength. So let's just keep that in mind. So when you have it closed on both ends, you have to have a node and a node here, and then maybe you have an antinode here. That's one possibility. You can have an antinode, maybe in the middle, antinode. Or maybe you have a node here, and then an antinode, and then another node in here. Okay. Or you can have you have to start with a node and end with a node. So the first possibility, you have node, antinode, node, or you can have node, antinode, node, antinode, and then you end with a node. So these are the possibilities, and then there is the next one, and so on. So let's see this first one here. Let me call it lambda 1, the first wavelength here, lambda 1. How long is it? Node, antinode, node, node, antinode, node, that's half a wavelength. So half a wavelength fits within a length L, so I have half of lambda 1 is equal to L, and therefore lambda 1 is equal to 2L. The next one will be, if I have the next case will be node, antinode, and then node, and then antinode, and then node. That's the next one. Because you always have to end with a node. If it's closed, again, the air cannot shake here. It has to be it's fixed in there. It can't move. So it gets to the wall and has to stop. So you have lambda 1 is 2L. Let's go to the next one. Let's call it lambda 3 here. So I have 1, 2, 3, 4 quarters of each of them is a quarter wavelength. So I can fit lambda 3. I'm sorry, lambda. Why did I jump? Lambda 2. Lambda 2 is equal to just L. So lambda 2 will equal to lambda 1 divided by 2. And so you have, and similarly, by the way, for the frequencies, F1 will be V over lambda 1, which is equal to V over 2L, V over 2L. And here, F2 will equal to V over lambda 2, which will be 2V over lambda 1 over lambda 1, and V over lambda 1 is F1, so that's twice F1. So F2 is twice F1, and the pattern continues. You can go lambda 3 and so on. So the conclusion will be that lambda m will equal to 2L divided by, or it's equal to, let me write it this way, lambda 1 divided by m, and that's equal to 2L divided by m, and Fm will equal to m times F1, and this number here, m, will equal to 1, 2, 3, and so on. Okay. The next one will be open, closed. So open on one end and closed on the other. Closed here and it's open here. So what do you do? So it's again length L. I'm sorry, let me consider the second case will be open, open. That's easier. Open, open, L. Length is L. Because it's very similar to this, and then we'll do the open, close. You take a wind instrument and like an open Coke bottle or something like a soda bottle, and you just blow in here, so the air has maximum disturbance here, and it has to have maximum here because it's free to move. So you can have here, it will be an antinode and another antinode at the end. Both of them have to be antinodes, but you can't go antinode to antinode without passing through a node, and so you have quarter wavelength plus quarter wavelength, so that's half a wavelength. So you have half of lambda 1 will equal to L. So lambda 1 will equal to 2L. So it's a similar situation to this. So you will end up with lambda m equals to m times, nope, it's equal to lambda 1 divided by m, and that's equal to 2L divided by m, and Fn or Fm will equal to m times F1, and in both of them m is equal to 1, 2, so on, 1, 2, 3, so on. So it's exactly the same. However, the only difference is for a closed on both ends you have node, node. Open on both ends you have antinode and an antinode on the other end. Now, when it's open on one end and closed on the other, so you come here and blow, and you get the air is moving here, so you have antinode. But here the air is fixed; it's a node. So you start with an antinode and end with a node, so that's a quarter wavelength. So lambda 1 will be, so that's a quarter wavelength. So a quarter of wavelength fits within a length L, so 1/4 of lambda 1 is equal to L. Therefore, lambda 1 will equal to 4L. You see now it's different. Instead of 2L, it's equal to 4L. I should say 1 here. And therefore, for example, F1 will be V over lambda 1, and that's equal to V over 4L. The next one will be, well, you start with a node. You start with antinode and end with a node. We did this one. So let's start with antinode and end with the next node here. So you have 1, 2, 3. So that's 3/4. Each of these steps is a quarter of a wavelength. So I have 3/4 of a wavelength of lambda. Should I call it lambda 2? Actually, let's call it lambda 3. For a reason that you will see in a moment. Let's just call it lambda 3. Doesn't matter what you label it, but it's easier to label it. Makes more sense to label it 3. Let's see why. It's equal to L, and that's equal, therefore lambda 1 will equal to 4L divided by 3, and that's lambda 1 over 3. Oh, I should say lambda 3. And that's why I labeled it as 3, because it's lambda 1 over 3. If I labeled it as lambda 2 equals to lambda 1 over 3, that would be fine, but this is easier to remember. Lambda 3 is lambda 1 over 3. And F3 will be 3F1, as you can easily verify. Because F3 will be V over lambda 3, and that's equal to 3F1. And then the next one will be to start with an antinode and end with a node. So here is antinode, node. We did this case. And then antinode, node. We did this case. Let's continue. Antinode, node. We did not do this case. So let's see. Quarter, 2, 3, 4, 5 quarters. So I'm going to call it 5/4 of lambda 5 equals to L. Therefore, lambda 5 will equal to 4L divided by 5, and that's lambda 1 over 5. You see, we skipped the 4 again because of, you can label it as 1, 3, 5, 7. The next one, as you can imagine, would be 7, because each time you're adding 2/4, so it would be, the next one would be 7. And F5 will be 5F1, and so we conclude that lambda M will equal to lambda 1 over M, and that's equal to 4L. Lambda 1 is not 2L, it's 4L for open closed, divided by M, and Fm will equal to M F1, but in this case, in addition to the 4L, the M's are 1, 3, 5, 7, the odd numbers. So that's that. Let's do an example on this. Let's do an example to simplify it. Here is an example from biology. The ear canal, obviously, your ear is open on one end for the air to get in, and then you have the eardrum on the other end, so it's closed on the other end. So it's open closed, and it's about 2.5 centimeters long. And so the question is, what would be the frequency of standing waves that we can hear in the air canal? What would be the frequency of standing waves in the air canal? The speed of sound in air is about 343. Let's say it's about 350 because the air is warm in the ear. So first of all, we have to select. It's the ear canal, so the length is L, and it's 2.5 centimeters. You can imagine this is like, you model it as your eardrum. You might say this doesn't look like an ear canal, it's kind of shaped differently, but to a good approximation, let's say it's open on one end, closed on the other end. You can add complications later, but for now, we have this. So we got L is 2.5 centimeters, 2.5 centimeters, and that is 0.025 meters. The speed of sound is about 350 meters per second. And we know that, so let's calculate lambda 1. Lambda 1 is 4L, is 4 times L. And 4 times 2.5 is 10 centimeters, so that's 0.1 meters. And so we get the first frequency that can resonate in the air will be V over lambda 1. So we get 350 over lambda 1. And that is 0.1. And that's 3,500 hertz. Okay. The next one will be F3. But right, the next one will be F3. We skipped the 2, it will be F3. and it's equal to 3 times f1, and 3 times f1 will be 3500 times 3, that's 10,500 hertz. And then f5 will be 5 times the 3500, that's close to about 20,000. That's the limit of hearing, because the frequencies that are audible to us are 3500 and are from 20 hertz to 20,000 hertz. So f5 is around the end of that range where we can hear. It's about 17,500 if you like. So I can write it. So 70,000. It's equal to 5f1. 5f1, and that's 17,500 hertz. You can try f7, but f7 will be above 20,000, and you cannot hear that. Okay. Now this particular frequency, this range, like 3,500, is particularly annoying to the human ear. You probably know, like if I scratch my fingers on the blackboard, that's about what frequency this of sound it creates, and that's why it resonates with the human ear, and it bothers it the most. And that's why we're very sensitive to that kind of sound. And let me go to my frequency generator here, the one I had for you, and I will show you, just making here 3,500. Let me see here. I'm going to here. I'm not sure whether you heard that or not, but it's that very annoying sound to us. Okay, so that is that. All right. So I want to summarize all of these on one side of the board because I want to do one more example. Let me get my eraser. So here it is. So closed, closed, open, open, they behave the same way. Open, closed behaved a little bit different. So open, open, and closed, closed. Just to remind you, closed, closed looked like this. Open, open looked like this. For both, you have lambda 1 is equal to 4L. I'm sorry, just 2L. And lambda n, or lambda m, in our book they use m. It's lambda 1 divided by n by m, and fm is equal to m times f1. And for open, closed, we had lambda 1 was equal, instead of 2L, it's 4L. And lambda m is equal to lambda 1 over m, very similar. And fm equals to m times f1, very similar again to this. However, the m itself is only 1, 3, and 5, and 7, and so on. Okay. So let's take an example here. I don't know much about musical instruments, but as far as we're concerned, you either have an instrument that's open on one end and closed on the other, or maybe open on both ends. So they say a clarinet is 66 centimeters, and it is, and a clarinet is open-closed, right? It's an open-closed tube. So a clarinet is 66 centimeters, so it's open, closed. So let's see here. The length, I think it says 66 centimeters. Let's see here, 66 centimeters. So L is 0.66 meters. This is the clarinet. And then a flute, it's open. It's open on both ends. And the length is 63.6 centimeters. 63.6 centimeters, yep. 63.6 or 0.636 meters. Okay. Let's take the speed of sound to be 350, just for simplicity, 350 meters per second. About 343 or so. And so the question is, what are the frequencies of the lowest note and the next higher harmonic on the flute and on the clarinet? Meaning, what is F1 and what is F2? By the way, lambda 1 or F1 is called the fundamental. It's called the fundamental. It's the first. And then the next one is called the higher, or the next ones are the higher harmonics. Okay, higher harmonics. So for the clarinet, it's open, closed. So we can use this. So we'll just say lambda 1 is equal to 4 times L. That's for the clarinet. 4L, and so we get, where's my calculator? So 0.66 times 4, 0.66 times 4, I get 2.64 meters. That's the wavelength. Therefore, F1 will be V over lambda 1, so that's 350 divided by 2.64, and we get, so 350 for V, so that over 360, over 2.64 times 350. So I get 133 hertz, that's F1. And then the next one will be not F2, it will be F3, because you jump one when it's open closed. So it will be 3F1. I mean, of course you can calculate lambda 3 and then do V over lambda 3 to get F3, but this is just easier. Once you find F1, the next ones are just multiples of it, either 3 or 5 or whatever. So 3 times this number here, and that gives me what? 399, I think? 399. Let me see, times 3. Approximately 399, 398 hertz. Okay. How about here? Open, open. So we get, first of all, lambda 1 is twice L, not 4L, twice L. This is open, open, or closed, closed. You get 2L. And so that's 2 times 0.636, and we get 0.636 times 2, gives me 1.272 meters. And so F1 will be V over lambda 1. You see, the speed of sound is only controlled by the medium. It's 350 here. Not by tension or anything. There are no strings here. And so 350 over that number. I have 275. About 275 hertz. Next one will be, is it F3 or F2? Well, let's see. Oh, here, I forgot to write. M is equal to 1, 2, 3, and so on. So the next one will be 2. For this one, the first one was 1, but the next one is 3. So this one will be twice. So F2 will be twice F1. So just multiply this number by 2, and you get yourself 550. 550 hertz. Okay. And so that is, that's that. Next, we're going to talk about interference in one dimension. We already talked about it when we added two waves. that is the interference. And so that would be when where you had the antinodes, that was the destructive interference, because the two waves canceled each other, you got a zero. And then the constructive interference is when the two amplitudes add up and that you create a larger wave. That would be the constructive interference. Okay, so that would be the next topic. And the idea is we will first look at waves in one dimension, and we will have waves traveling in one dimension, and they are also traveling in the same direction, and they might have a different phase shift. That would be the idea. Okay, I will see you in the next video for interference in one dimension.